Hello everyone, my name is Enrique García-Macías. I'm from the Department of Civil and Environmental Engineering at the University of Perugia in Italy, and it's a pleasure for me to present this work entitled Sparse Multiple Regression for Efficient Damage Identification of the Consoli Palace in Gubbio, Italy. Well, this is the outline of this talk. First, I will give you a brief introduction and motivation for this work, followed by some details about the theoretical background and some numerical results we obtained in the Consoli Palace in Gubbio. Finally, I will conclude this presentation with some concluding remarks. The motivation of this work arises as a result of some monitoring works we have been conducting in the Consoli Palace in the last years. The Consoli Palace is the most emblematic building in the medieval town of Gubbio in central Italy. Built in the 14th century to host the courts of the city of Gubbio, the palace houses the civic museum of the city since the early 90s. As an extraordinary example of a monumental masonry building, the palace has been the benchmark case study of a number of research projects, including the Horizon 2020 Heracles project and a national print project devoted to the detection of aging and degradation in historical masonry structures. As a result, a structure health monitoring system was installed in the palace and it has been acquiring monitoring data continuously since 2017. To better illustrate the SHN system installed in the palace, let me show you a short YouTube video we have created to disseminate some of the scientific achievements we have made in the palace so far. Let me first mention that all the monitoring data recorded in the palace have been processed into software codes developed by the research group, named MOVA and MOS. MOVA is devoted to operational model analysis, that is dynamic identification of structures, while MOS manages complete SHN systems and conducts damage detection. The monitoring system in the palace was upgraded in 2020 and it comprises 12 high-sensitivity accelerometers, 4 LVDTs to monitor displacements of 2 cracks in the palace, and 6 temperature sensors. Up to 9 resonant frequencies have been continuously identified in the frequency range up to 10 Hz. Now the video shows the graphical output of MOS with the continuous assessment of the palace. In particular, the code shows the time series of resonant frequencies of the palace, time series of dynamic, static, and environmental monitoring data, and a control chart for damage detection. Well, everything in the system was functioning normally until May 2021, when a major anomaly was detected by the software. The anomaly was triggered by a near-field seismic sequence initiated on the 15th of May with 6 different events with maximum moment magnitude of 4. The identification of this anomaly and, most importantly, the quantification of the earthquake-induced damage was not an easy task at all, and this gave origin to this work. And to understand these difficulties, we must be aware of the underlying process to conduct damage identification. It is well known that the dynamic properties of masonry structures are highly affected by environmental conditions, and therefore it is essential to eliminate such effects to unveil the presence of damage. This is commonly done within a pattern recognition approach, where a statistical model is trained to reproduce the dynamic features of the structure using certain in-control dataset, also called training period, where the structure is assumed to remain healthy. Therefore, this model can be used in the damage assessment period to predict the modal signatures of the structure if remain healthy. The initiation of damage can be inferred from the residuals, that is, the differences between the experimental data and the predictions of the model. Nevertheless, most state-of-the-art pattern recognition approaches suffer from 2 major limitations: sensitivity to the presence of outliers in the investigated features, and the selection of predictors to train the statistical model. These 2 aspects resulted in critical limitations to identify the earthquake-induced damage in the Consoli Palace, and this motivated the development of a new pattern recognition approach that we present in this work. The proposed approach is aimed at tackling the aforementioned limitations, minimization of outliers in the training period, and an optimal selection of predictors. To do so, a new approach combining the minimum covariance determinant method and least angle regression is proposed for optimal multiple linear regression. This translates into the methodology sketched in the slide. The training period of selected features, in this case the resonant frequencies obtained by operational model analysis, is first cleansed using MCD. Then an optimal set of predictors is selected using LAR. The resulting multiple linear regression model is used to perform damage detection and quantification through novelty analysis.
Let me give you now some details about the theoretical basis of the MCD and LAR algorithms implemented in the proposed methodology. The MCD method was introduced by Rousseau in 1984 as a robust estimator of multivariate location and scatter. This method assumes that the dataset under study, in this case the training period, is normally distributed. Then the final goal of the algorithm is to find a subset of a given size with lowest covariance. Let's start with a subset H1 composed of H samples taken randomly from the training period. Then the Mahalanobis distances of all the samples with respect to the previously selected subset are computed. Finally, the samples are sorted according to these distances, and a second subset can be defined by taking those samples with minimum Mahalanobis distances. This process, also known as the concentration step or the C step, yields a second subset with equal or lower covariance. This process can be carried out iteratively, leading to a non-negative sequence of data subsets with lower and lower covariances. It can be proved that after a finite number of steps, the algorithm always converges to the dataset with minimum covariance. To avoid the dependence on the initial subset H1, the fast MCD algorithm proposed by Rousseau and Andreasen has been implemented in this work. Once the optimal subset has been defined, the data points with maximum Mahalanobis distances with respect to this subset can be considered as outliers. And finally, once the training period is free of outliers, a multiple linear regression model can be trained to reproduce the environmental effects upon the features under study. This is accomplished by building up an observation matrix X composed of certain predictors which may comprise a variety of environmental factors such as temperature, humidity, wind, etc. Then a vector of coefficients beta is fitted in some way to minimize the differences between the model output and the experimental data. The quality of the model is highly dependent on the selected predictors in X, which motivates the implementation of the LAR algorithm. The LAR algorithm, developed by Efron and co-authors, is an efficient algorithm for model selection of sparse linear models. It considers that some of the predictors in X can be non-representative of the variability in Y, and therefore their beta coefficients can be zero. Let's illustrate this algorithm with a simple example of three covariates x1, x2, and x3. The algorithm starts by setting the coefficients vector to 0. Then the first covariate to be included in the regression is the one with the largest correlation with the residual, which in this first step is the output variable y. In this example, this corresponds to x1. Then the regression coefficients vector is moved towards its least square value until some other predictor has as much correlation with the current residual. This movement can be interpreted as the equiangular direction between the predictors and the current residual. Then the covariate with the least angle is selected. In this example, this corresponds to the angle between x1 and x3, which determines the first regression coefficient. This process is repeated until the full least square solution is achieved. This leads to a set of linear models with decreasing level of sparsity, being possible to select the optimal one using a certain quality metric.
Let's go now with the numerical results. These are the time series of resonant frequencies of the Consoli Palace. As mentioned before, 9 modes were consistently tracked throughout the monitoring period from July 2020 until July 2021. An automated OMA procedure based on covariance-based stochastic subspace identification was used in most. Interested colleagues may find further details about the procedure and the software codes MOV and MOS in the reference shown in the slide. The training period has been defined until the 1st of May of 2021, around 9 months of data, followed by the damage assessment period until July 2021. In this slide, I show the correlation analysis between the first 6 resonant frequencies and the environmental temperature registered by a thermocouple located in the second floor of the palace. It is observed that some correlations are highly nonlinear, which evidences the difficulties involved in the selection of the predictors for the subsequent pattern recognition. Afterwards, the MCD algorithm has been applied to the time series of resonant frequencies in the training period. In this work, 20% of the data samples with maximum Mahalanobis distances are considered as outliers and indicated by red data points. Based upon the cleansed dataset, the LAR algorithm has been applied to build the statistical model for pattern recognition. In the analysis, a total of 48 potential predictors have been considered.
These include linear and quadratic versions of the time series of environmental temperatures recorded by 3 thermocouple. Additionally, with the aim of accommodating potential thermal capacitance effects in the palace, time-delayed versions of the previous time series have been also accounted for. These include delays of 30 minutes, 1 hour, 2 hours, 5 hours, 12 hours, 24 hours, and 48 hours. In the figure in the slide, the coefficients of the large regressions of the fundamental frequency of the palace are shown. This figure shows the norm of the coefficients vector versus the beta coefficients. And it is noted how the number of predictors with non-zero regression coefficients increases as the large algorithm progresses. Once the family of sparse models is obtained, the optimal model has been selected as a solution with minimal Bayesian information criterion. In the following figure, the residuals between the experimental results and the predictions of the statistical model are shown. It is noted that the residuals almost follow a perfect Gaussian distribution with a skewness value of almost 0 and kurtosis around 3. The previous procedure has been applied to the resonant frequencies of modes 1, 3, 4, 5, 7, and 9. In the figure in the slide, the time series of resonant frequencies are compared with the predictions of the statistical model. In the zoom views of the right-hand side of the slide, it is evident that after the seismic sequence of May, the resonant frequencies experienced a sudden decay. This trend is not captured by the statistical model, and the differences, that is, the residuals, can be exploited to detect and quantify the earthquake-induced damage in the palace. The Hoteling's control chart in the bottom left side of the slide shows a sudden increase in the number of out-of-control data points. Specifically, considering an upper control limit of 95% confidence level, the number of out-of-control data points increases up to 72% after the seismic sequence. The quality of the classification has been evaluated in terms of rock curves. These results show that the proposed approach approximates the perfect classifier independently from the number of modes taken into account in the classification. The obtained residuals have been used to quantify the earthquake-induced decays, specifically to facilitate the identification of shifts and minimize the effects of residual variance. The convergence of the average of the residuals before and after the seismic sequence has been considered, as represented with dashed yellow lines in the figure in the slide. The mean convergence curves suggest certain stabilization, which allows to state the appearance of persistent damage in the palace. These results also allowed us to investigate the variations in the correlations between the resonant frequencies and the environmental temperature. Note in this figure that the third mode, which is a bending mode of the bell tower of the palace, experiences a clear shift for all the temperature range. Finally, the outcome of this analysis was used to quantify the earthquake-induced decays in the resonant frequencies of the palace by means of a bootstrap approach. The obtained results showed that the earthquake-induced damage concentrated in modes 3 and 5, with maximum decays of 2%. These modes correspond to a bending mode of the bell tower and the global torsional mode of the main body of the building. Given the relative orientation of the palace with respect to the propagation direction of the seismic shocks, it is expected that damage will concentrate in the north facade of the palace, which agrees with the obtained decays. It is interesting to observe that no significant variations were found in the MAC values between the mode shapes before and after the seismic sequence, with values very close to 1. This circumstance may indicate that the damage is very moderate and sustains no severe structural risk to the palace. In fact, preliminary in situ inspections have not revealed any new pathology in the palace, which suggests that the developed damage remains at a degree not observable by visual examinations. And finally, let's finish this presentation with some concluding remarks. This work has proposed a new damage identification method combining data cleansing and sparse multivariate regression. The presented results have demonstrated the ability of this method to automatically handle large datasets of predictors, including both static and dynamic variables. Maximum earthquake-induced decays of 2% have been found in the global torsional mode of the palace and the first bending mode of the bell tower. And finally, no significant variations have been found in the mode shapes of the palace, which along with some in situ inspections allowed us to conclude that the damage condition remains at an early stage of development with no critical risk to the integrity of the building.
And that's all. Many thanks for your attention. I hope you enjoyed the presentation. If anybody in the audience has any questions, I will be more than pleased to answer them. And also in the slide you can find my email address if you want to get in contact with me. Thanks again. Bye.